So in section 2 of chapter 1, we're going to look at represented quantitative variables with graphs. And we're going to take a look at a few different types of graphs today, specifically 4, that we can use as quantitative variables. And we'll take a look at a couple more next week when we're looking at 2 variables as well. So the first thing we're going to look at are histograms. So in our first example here, we have combined scores for 2 weeks of NFL games. So it's a team's score for 2 weeks. So in our table, we have 32 different combined scores. In order to make a histogram, it's similar to a bar chart, except the bars are going to touch. So in order to get the bars to touch, we have to have specific widths, and they're called bins. I prefer to call them classes. Okay. And these classes have to be the same width. And this width is determined in a couple different ways. You need to know how big of a range you have for your data values, and you need to know what is going to make sense. So the smaller the range in data values you have, so if you have numbers that are a lot closer together, you're going to have smaller bins. You're going to want to make sure you have smaller ranges. The larger number of values you have in your data set, the larger the classes are going to be to kind of spread it out more. So in our table, we have the smallest score is 16 and the largest score is 72. So it's a pretty good width, and we want to come up with a pretty nice size that's going to give us a pretty good distribution, and that size is going to be 9. So we're going to start at 15 because I don't need to start at 0. We're going to go 15 to 24, 25 to 34, 35 to 44, so on and so forth. So what I'm going to go do now is go through the table and figure out how many numbers are in each of our classes. And as I do that, I'm going to cross them out of the table so that I know that I've used them once. So the first thing I'm looking through are numbers between 15 and 24. Which there are 4 of. Next, I'm looking for numbers between 25 and 34. Which there are 3 of. Next, 35 to 44. Which there are 13. Now 45 to 54. Which there are 6. Next, 55 to 64. Which there are 3. 65 to 74, which there are 2, and then 75 to 84, which there is 1. And then just double check, I can add up my numbers in each class to figure out, to make sure that I have 32 numbers, in which case I do. So now I'm going to go ahead and create the histogram. So to create the histogram, I have to label it just like I did a bar chart. So the y-axis is going to be our count, and the x-axis is going to be what our data is looking at, which in this case is NFL scores. So I'm going to make my y-scale first, which I'm going to go up by 2, so I'm going to go from 2 to 14. And when I'm creating my x-axis, what I'm going to do first is I'm going to skip 0 to 15, 0 to 14, because I don't have any values in that first class, so I don't need it. So I'm going to use the symbol to indicate I've skipped those numbers, and then I'm going to start at 15. Now, when I'm labeling my x-axis, I start with the first number of each class. So that's going to be 15, 25, 35, 45, 55, 65, 75, and then 85, because I do need an ending number for my last class. Now I'm going to go ahead and create the bars. So 15 to 24 has a height of 50, so I'm going to go up to 4. Now one thing we need to make sure we discuss with histograms is, because all the bars are going to touch, when I'm trying to figure out what numbers are actually contained within each class, I include the first number, so the number on the left, but when the class ends, the number on the right, we don't include it. So it's assumed that when I draw my first class, even though it goes from 15 to 25, 25 isn't actually in that class. It's in the next one. So 25 to 35 is going to be 3. 35 to 45 is going to be 13. 45 to 55 is 6. 55 to 65 is 3. 65 to 75 is 2. And then 75 to 85 is 1. So there's a couple nice things about histograms. The most important one being that you get a good idea of the distribution of the data. And we'll talk more about distribution shapes in the next section, but you can get an idea of like what the distribution follows. You can figure out where most of the values occur. But other than that, histograms aren't great for a lot of things, because unless you have the data to look back at, there's not a lot of inferences you can make about statistical data, such as mean, median, mode. We'll talk about standard deviation as well. Those things you can't tell from a histogram because you don't have access to each data value in itself. 15 to 25 means, and because my count is 4, those 4 numbers could be any value within that class. They could all be 15. They could be 15, 18, 19, 20. You really don't know unless you have access to the data itself. Another thing with histograms is that they can be time consuming, especially if you have a large set of data. This 32, not in an excessively large set of data, so we could do it by hand. We're also going to discuss how we can do this in a graphing calculator. So this next page, go ahead, pause the video as much as you can, follow along on your own doing this in your graphing calculator. If you get stuck with anything or have questions, please let me know and I can walk you through it. So the first thing you need to do is enter the data in your calculator. And the way you're going to do that is you're going to go to Stat and then Edit. And Edit is the first thing that happens when you hit Stat, so you're basically just going to hit Enter. And then you're going to enter the data into list 1. So after you type a number, you're going to hit Enter, and then you're going to type another number, and then you're going to hit Enter. So the list does go down, not horizontal. I'm going to enter your numbers vertically. If you already have data in list 1, you go to the top, you highlight L1, then you hit Clear, and then you hit Enter. Next, we're going to go ahead and graph our histogram. So we want to press Stat Plot, which on your calculator is going to be second and then Y equals. You are then going to choose Plot 1. You're going to hit Enter. You're going to highlight the On box and hit Enter. You're going to go down to Type and you're going to choose Histogram, which is the one that looks like a bar graph. And then that automatically should change your X list to L1 because that's where the data is. If you have your list in you have your data in a different list, let me know and I can tell you how to change it. And you should have something directly on the right. If you have a graph already in Y equals, you need to clear it. If your other plots are on as well, you need to make sure they're turned off. So if you run into any of those issues, please let me know. I can help you do that. Now you're going to create the histogram itself. So you're going to choose Zoom and then 9. And it will make the calculator create a histogram. Now, that histogram may not be the exact classes that we want. So we can adjust that. And we're going to go to Window. And we're going to make it use the values we did on the previous page. So we're going to set our X min to 15, our X max to 85, and our X scale to 10. We can also adjust the Y. So we're going to change our Y min to 0, our Y max to 14, and then our Y scale to 2. And then we'll press graph. And then we'll have a new histogram that looks just like the one we had on the previous page. You can also determine from a histogram how tall each of the classes are by selecting trace. So if you select trace, it automatically creates a dot at the top of each of those bars, and you can use the left and right arrows to go to each one and see how many values are in it. So I previously talked about this a little bit, but when we're talking about the widths of our classes, you can make it too large or to get too few of your classes, or you can make the width too small and get too many. So in the picture here, the left side has a width of 3 for this data, which would be, 25, which would make only 3 classes, while the right has a width of 3, giving us way too many. So the best way to start is by doing zoom 9 and then going into window and making adjustments as needed. Next, we're going to look at stem and leaf plots. So in class, we gathered data about pulse rate. So we either used the artery on the inside of our wrist or our carotid, found our pulse for 20 seconds at a time, 3 times, and then we tripled it. Then we found the average of those 3 numbers. And what I have below is some class data for 15 students, and along with their gender and their average of their tripled data. So if you need to go ahead and pause the video here to copy down the data, please do so, so you have it in your notes. So a stem and leaf plot is an alternate way of illustrating data using, it's kind of like a graph, but it still involves using our data as numbers. So it's similar to a histogram, but unlike a histogram, when we graph it, we lose the data. In a stem and leaf plot, we don't. So typically when it comes to doing stem and leaf plots, if the data has 2 digits, the stem is our tens place and the leaf is the ones place. If it's 3 digits, the stem is the tens, the hundreds and the tens, and then leaf is the third. If we're dealing with decimals, the stem is the ones place and the leaf is the tenths place. So it really just depends on the data. So we're going to create a stem plot for the pulse rates in the table above. And then we have to make sure we add a key so that other people, when reading it, know how to identify the data. So if I'm looking at the pulse rates, my lowest value is 55 and my highest value is, I believe, 94. So when I'm determining my stems, I'm going to start with 5 and then I'm going to go 6, 7, 8, 9. So I have 50, 60, 70, 80, and 90s. Now I'm going to fill in the ones place of every value that fits in that range. So there was only one person whose heart rate was in the 50s, and theirs was a 55, so I just write a 5. Next, I move on to the 60s. So we had a 60, so I'm going to put 0. Then we had a 63 and a 65 and a 66. Then we're going to move on to the 70s, which was there was a 73, a 74, a 75, a 77, a 78, and 2 79s. Now, if I have a number that's repeated, I don't just write it once. I will write it twice because I have to account for all the data so that every number appears in my stem and leaf plot. Next would be 80s, which we didn't have anyone whose heart rate was in the 80s. So I still put the 8 there, but I just won't put any values to the right of it because nothing is in there. And then we end with our 90s. So we had a 90. And then we had a 94. And then just to double check that I had all the numbers, and then we count and make sure I have 15. I missed a number. I missed the 68, so I'm going to go ahead and add the 68 here. So there we go. Now I have accounted for all the values. So just like with a histogram, when we start to talk about distribution shapes, if I kind of turn to the stem and leaf plot, so my stems are kind of like an x-axis and the leaves are kind of like a y-axis, I can get an idea of a shape. Unlike histograms, though, with stem and leaf plots, I can also figure out mean, median, mode, and even standard deviation because I have access to all of the data in the graph. So you can do more mathematically with a stem plot than you can with a histogram. There is also something called a split stem and leaf plot. So what it is if you have too many data values in a single stem, it can skew what the distribution actually looks like. So what we do then is we split the stems. Usually they're split as a 0 to 4, 5 to 9 type. But if you have a lot of data and a very close range, you may split it further. You may go 0 to 1, 2 to 3, 4 to 5, or even 3, 0, 1, 2, 3, 4, 5. So the way you split it is really dependent on how many values you have and how close they are all together. So the data we're going to look at first is scores from a Unit 1 test, and there are 24 numbers. So typically speaking, when you're breaking up a stem and leaf plot, we break it up, like I said before, 0 to 4s, 5 to 9. So what I'm going to do is I'm going to break it up, my lowest score being a 62. I'm going to break it up so that one stem is 60 to 64, the next one is 65 to 69, so on and so forth. So I need 2 of every tens place starting with 6. So 6, 6, 7, 7, 8, 8, 9, 9. Now I don't need a 10 here because no one got 100%, so I don't have to do a 10. So my first leaves are going to be anything between 60 and 64, which I think there was just the 62. Then I'm going to do anything from 65 to 69, which I believe there was just the 69. Next we move on to the 70s. We're going to do anything between 70 and 74, of which there is a 74. Then we're going to do 75 to 79, which there is a 75 and a 79. Now we're going to move to the 80s. So my first one is going to be 80 to 84. And there is an 80, so I have a 0. There's an 82. There are 2 84s. I missed a 78. So we have a 78 and a 79. This is why I like to cross the numbers off to make sure I don't miss any. All right, next we're going to move 85 to 89. And I missed a second 80. Let me fix that. Okay, now the 85 to 89, which I believe there are 5 88s and that's it. I missed a third 80. Let me add another 80. Okay. Now we're going to do the 90. So 90 to 94. So there's a 90 and another 90 two 92s, third 92, a 93 and a 94. And then the last one is just a 96. Just to double check, I'm going to double check I have 24 numbers. $25 numbers. So in looking over my data, I realized there were only two 80s. I just counted one of them twice. So I'm going to go ahead and get rid of one of them. So now we're back down to 25. See, it's very important that you're checking yourself to make sure you have it correctly. And I do realize that I forgot to make the key on our last example. So after I do the key for this one, if you want to go back and make it yourself. So when we're looking at a key, when we're creating a key, it's so that someone else, when reading it, they can see what our stem and leaf plot represents without having access to our data. So I'm going to use that 9 bar 2 is the value 92. It is also important that you include units if the problem has them. So in this case, because we're looking at test scores, it's just a number. We don't really have units. So it's just going to be 92. The previous example, when we were looking at heart rate, does have units. It's beats per minute. So when you do your key for that, you're going to want to make sure you include beats per minute. So the benefit to doing a split stem here was that once we got to the 80s and the 90s, we found that there were a lot of values in that range. And if I hadn't split it up and I had just done 6, 7, 8, 9, I would have had very long leaves when I got to 8 and 9, which will skew the distribution and maybe not give us an accurate look at what the distribution actually is. So splitting your stem and leaf plot can actually be very beneficial. Next, we have a dot plot, which is one of my favorite because it's very easy and very straightforward. So you plot the data values with dots above a corresponding value on a number line. So when you're constructing a dot plot, you only need to label your x-axis, and typically the x-axis is the title of the graph. So if those match, you don't need to double name it. But if your x-axis and your title don't match, you'll need both. So what we do is we draw a horizontal line, we label it, and then we scale it based on the data we're given, and then we mark dots above the number along the number line. If we have multiple values, we just keep placing dots above it. So we have quiz scores out of 50 on a past exam, and we want to construct a dot plot based on this data. So my x-axis is going to represent my quiz scores. Now you can come up with your own scale for this. You can go up by 2s. I would not go up by 1s, but you can go up by 2s, 5s, however you want. I'm going to go up by 5 since my line is a little bit shorter, but if you want to make your line for your number line a little bit longer so you could go up by 2s, go for it. So it looks like the lowest score on the test was a 26, and the highest was a 50. So I'm going to go up by 5s, and I'm going to start with 25. So I'm going from 25 to 50. So 25, 30, 35, 40, 45, and my 50 is just a little bit too far away. Now, another nice thing about a dot plot is that you do not have to organize the numbers. You can just go as they appear. So my first dot is going to be above 36, and then I'm going to continue on. So there are 4 dots above 42, and 26, 38, 32, 30, another one above 42, 34, 44, 44, 34, 48, another 2 over 42, another 34, 38, 50, 3 more 38s, and then another 44. So nice thing about dot plots, they're pretty quick. Even if you have a larger data set, dot plots are still very quick. You also, just like with a histogram and a stem and leaf plot, get a great idea of what the distribution looks like. Just like stem and leaf plots, as long as, depending on how you do your scale, like if I had gone up by 2s, it would be a lot more accurate. I have access to all of the data. I can find mean, median mode, and standard deviation as well. That's more based on what your scale looks like on your x-axis. Because I went up by 5s, it's a little bit more difficult, but if I'd gone up by 2s, it would have been exact and it would have been perfect. The last type of graph we're going to look at is a cumulative relative frequency graph. Also known as an ogive or an ogive, I'm not 100% on the pronunciation. It displays percentiles. So if you're dealing with percentiles, this is the graph you want to use. If you're not already dealing in percentiles, I wouldn't use this graph. So just a refresher, a percentile tells you what percent of data falls below a value. And depending on what your data looks at, determines if a percentile is a good one or not. If you're in the 99th percentile for height, that's great. It means you're tall, people are shorter than you. If you're in the 99th percentile for cholesterol, that's bad. It means you have a really high cholesterol. It's very unhealthy. You should probably see a doctor. So percentiles are all relative based on what you're talking about. So there are a couple of different ways to create the graph for a cumulative relative frequency. It does require you making a table, and you can do the table one of two ways. You can find relative frequencies and then find cumulative percentages, or you can find cumulative frequencies and convert those to percentages. And I like the second way better. It's just a tad bit more accurate, as you'll see when we look at the example, but both of them are acceptable, and as you will see in a little bit, they both give the exact same graph. So in the tables that we're going to look at, for example, we have the ages of the first 45 U.S. presidents when they took office. So Joe Biden is not included. It only goes up till Donald Trump. Just a couple fun facts. Donald Trump was the 45th president and was the oldest sworn in at 70 years old, and Teddy Roosevelt, the 26th president, was the youngest at 42. So we can see with, similar to histograms, cumulative relative frequency graphs have ranges, and they do need to be equal, just like with histograms. So my age ranges are broken up by 5s. So 40 to 44, 45 to 59, 50 to 54, 55 to 59, 60 to 64, 65 to 69, and 70 to 74. And then the frequency, so 2, 7, 13, 12, 7, 3, and 1. So the frequency are the number of presidents that fit within that range. So when we're looking at relative frequency, what we're looking at is the number over the total represented as a fraction. So we already know we're looking at 45 U.S. presidents. So the relative frequency for the first range is 2 out of 45, which as a percentage is 4.4%. My next one is 7 out of 45, which is 15.6%. Next we have 13 out of 45, which is 28.9%. Then 12 out of 45, which is 26.7%. 7 out of 45, again, which is 15.6%. 3 out of 45 is 6.7%. And then lastly, we have 1 out of 45, which is 2.2%. For a cumulative relative frequency, we add the fraction, we add the percentages as we go. So the cumulative relative frequency says how much of the total percent has occurred so far. So the first range is always going to stay the same because that's the only amount that's occurred so far. So the first one is still 4.4%. Okay, but then I'm going to add it with the next percentage to figure out how many have occurred up to the 49. So we're going to do 4.4 plus 15.9, which gives me 15.6, I'm sorry, 20% exactly. So I can say 20% of all presidents were between 40 and 49. So it includes both. Then we add that to the next percentage, and we get 48.9%. So 48.9% of all presidents are between 40 and 54. So you get the idea, and we're going to continue that trend for the rest. So 48.9 plus 26.7 gives us 75.6. Then we add 15.6, and we get 91.2 plus 6.7, which is 97.9. And then here's where you can see why this one is not as accurate. I actually, when I add 2.2 to 97.9, get 100.1%, which we're going to say is about 100% because we can't have over 100% of something. And I'll explain why this is less accurate as we're doing the next example. And so you can see some big jumps. We know that most of the presidents are between 40 and 59 because 75% of the data happens there. And then there's a big jump, there's a fairly decent jump from the 55 to the 60 to 64. And then not a lot of change from the last. There's not a lot of presidents that are over 64 when they take office. The reverse side of the thing, the second way, to find the cumulative frequencies and convert those to percentages. So cumulative frequency is adding fractions. So instead of making fractions individually, then finding a percent, then adding percentages, we add the fractions first and then just find what percent that fraction is, which is a little bit easier and a little bit more accurate. So similar to the example we did before, the first one stays the same. So it's just 2 out of 45. Nothing has occurred so far. To get my next fraction, I then add the next frequency. So 2 plus 7 is going to give me 9 out of 45. Then I add the next frequency, which is 13, so I get 22 out of 45. So now I'm just adding the numbers to get my new fraction. So 22 plus 12 is 33 out of 45. Plus 7 is, I made a mistake adding. 22 plus 12 is 34. So 34 out of 45. Plus 7 is 41 out of 45. Plus 3 is 44 over 45. And then plus 1 is 45 over 45. I like this way a little bit better because your last fraction should be the total over the total, so that you know you've added correctly. Now I can figure out what percent that fraction is. 2 out of 45 is still 4.4%. 9 out of 45 is still going to be exactly 20%. 22 out of 45 is still 48.9%. 34 out of 45 is still 75.6%, but 41 out of 45 is 91.1%. So you can see that this is where that extra 0.1 came from. Because I was dealing with decimals based off the fractions and then adding those, it counted for a little bit of error that occurred. And then 44 out of 45 is 97.8. And then lastly, 45 out of 45 is 100%. So it still tells me the exact same thing. 75.6% of all U.S. presidents, when they were elected, were between 40 and 59%, 40 and 59 years of age. So I get the exact same percentages with a little bit of room for error, and it tells me the exact same thing. Let's see, 20%. Sorry, the relative frequency, not the cumulative relative frequency. It uses the relative. So when we look at the graphs, we get the same percentages, and the graphs look exactly the same. It can look like a histogram or a line graph. I prefer the line graph, so I'm not going to do the histogram because I prefer the line graph. So you can see that the y-axis is always the relative cumulative frequency. So it's the percentage that you get in that bottom row of either table. And then the x-axis is our age at inauguration. And then I'm just keeping track of the percentages as we go. So at 40, and you'll see here we use the lower value in the range as our starting point. So at 40, we were at 2.2%. So it's almost at 4.4%, excuse me. So it's almost at 0. Then our next range started at 45, which jumped up to frequency. So then it jumped up to tiny little percent. So you can see the percentages grow. And if you wanted to create a histogram, it's really not that difficult. You just make bars going to where each dot is, where each percentage ended. So it's really, they grow, and you can kind of see where trends occur. So you can see where biggest jumps occur, where there's little change. Like there was a big jump between the 45 and from 45 to 50 and 50 to 55. Pretty similar jump from the 55 to 60, but very little increase after that. So you can get an idea of where larger increases occur, which kind of gives you an idea of where most of the presidents' ages fell. Let me know if you have questions about the cumulative relative frequency graph or any of the graphs. If you need help with the calculator, please reach out.